In lab, you guys looked at several compounds, ionic and covalent, or ionic compounds and molecular compounds, and you noticed some properties of both. Now, hopefully what you noticed was that every single ionic compound you looked at happened to be solid. And that's actually due to an innate property of ionic compounds. Remember, ionic compounds contain ionic bonds, which are formed when electrons are transferred from one atom to another, and that means we're going to have strong attractions between oppositely charged ions. Okay, those ions stick together in as solid as a crystal. Now think about this. If you have a positive ion, it's going to attract negative ions, and a negative ion is going to attract positive ions, negative, positive, negative, positive, negative, positive. And that process repeats in every direction. Okay? So when we have an ionic compound, we actually have a crystal, and this crystal can get as big as it wants. As long as there's more ions around, the crystal can keep growing, which means this could be sodium chloride, NaCl. It could be aluminum chloride, AlCl3. I don't really know. I guess I have a 1-to-1 ratio of charge here. It's easier to draw it that way. But this crystal can keep getting bigger. So let's say this is sodium chloride, NaCl. This is a 1-to-1 ratio because for every positive sodium ion there's a negative chlorine ion, and this is why it's a solid. These large attractions hold this together in a crystal. But this is different than a molecular formula, right? This is not telling me in sodium chloride there's 1 ion of sodium and 1 ion of chlorine and that's it. It's saying in a crystal of sodium chloride there's 1 ion of sodium to 1 ion of chlorine. The ratio stays the same throughout, 1 to 1 to 1 to 1 to 1. Okay? So this crystal can just keep getting bigger as long as there's more ions, and it can just keep growing and growing. And no matter what, it's always going to keep the same shape, the same structure, the same ratio of ions, sodium to chlorine. Because of that crystal structure and the strong attractions between those oppositely charged ions, ionic compounds tend to be solids with high melting points. Remember, it's the forces of attraction and the particle speed that determine something's state. So we know solids tend to line up like this, and liquids are close to each other, but they don't have any definite order or shape because they can slide past each other. And we know gases bounce all over the place. They can spread out and move. Okay? Well, because there's high attractions between positive ions and negative ions, these things tend to be solids and tend to have very high melting points. Salt, for instance, has a melting point around 800 degrees Celsius. Really, really warm. Okay? They're brittle. They shatter easily, and this is due to their crystal structure. Right? If I have a plus minus, 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 and somebody comes along and smashes this crystal, just hits the bejeepers out of it with a hammer. Well, think about what that does. That shoves this crystal down. So now instead of plus minus, plus minus, plus minus, I have plus minus, plus, plus minus, plus minus plus minus minus. Okay, so right here where this got hit, that's going to be a repulsive force because a positive doesn't want to be with a positive, and that's going to shatter off. So they're brittle because striking them misaligns the crystal structure and opposite charges repel. The conductivity, this is something you actually measured in lab. Hopefully what you noticed was that these were good conductors. The more ions that were present, the higher the conductivity. But we didn't test them as solids. Okay, this right here, a crystal, will not conduct electricity very well. Electricity is the flow of charged particles. Electricity is simply the flow of charge. There are no charged particles available to flow in an ionic solid because every one of these little ions is locked in position. Nothing's going to move, it's not going to go anywhere. So as a solid, it doesn't conduct very well. However, if you dissolve it, okay, when you dissolve an ionic compound, you have your beaker full of water. These little plus minus things, you notice when they dissolved, you couldn't see them anymore. And that's because the ions actually split apart from each other and they were carried around by the water solution and separated from each other. And so now you have free plus and minuses that are actually free to move around, which explains why they can conduct, because now charge can flow. Now the molecular compounds that you guys looked at, or the covalently bonded things, behaved slightly differently. Remember, molecules contain elements held together with covalent bonds, and in a covalent bond, electrons are shared, they are not transferred. Now molecules are different from ions because ions are crystals and crystals can just keep getting bigger. But molecules are not crystals and they don't just keep getting bigger. They form a molecule and that molecule is done. That's it. That's as big as it gets. So when we have water, H2O, it's one hydrogen atom, one oxygen atom, one hydrogen atom, and that's it. There's 4 atoms in that thing, and that's, or 3 atoms in that thing. That's as big as that molecule gets. If we add more hydrogen and oxygen to this, we'll get another oxygen and another hydrogen and another hydrogen. They'll stick together, they'll make me another water molecule, but those are distinct and separate molecules. They are separate from each other. There are no bonds between them. Okay? So in H2O, that's actually telling me one molecule of water has exactly 2 hydrogen atoms and 1 oxygen atom. It is not a ratio, it's actually counting atoms. Same thing with carbon dioxide, CO2, and that's why we use the prefixes for molecules. It's counting atoms in a molecule. Okay. Small molecules tend to be liquids or gases at room temperature. And you think about that, remember the state of matter is determined by the attractive forces as well as the speed of the particles. Well, if these things are little, like water, it's a liquid at room temperature, they're going to be moving fairly quickly, so it's going to be hard for them to be held together as a solid. Another one, oxygen, O2, that's a molecule. It's a gas at room temperature. In fact, it's a gas at temperatures well below room temperature. These things are little, they're not very big. There's only a couple atoms, and there's weak forces of attraction between a lot of them. Okay, larger molecules tend to be liquid or solid at room temperature. One of the molecules that you guys will learn about is a thing called a triglyceride or a fat. Okay, and basically, it's got a huge chain of atoms. This just keeps going and going, and then you have a similar thing here. Okay, and this is called a triglyceride. It's a lipid, and depending on how long these chains of carbon atoms get over here, this thing can be a liquid or solid, but this can just keep growing and growing and growing. So when I say molecules can be hundreds of atoms, they can be hundreds of atoms. These things can be really, really big. And if you have a whole bunch of these molecules, they're going to tend to stick together, and depending on exactly how big this gets and some of the shapes of things, this can be a liquid or a solid at room temperature. In fact, asphalt is a molecular compound. It's a mixture of a whole bunch of different molecular compounds. They're solid at room temperature. But if you've ever walked across asphalt on a hot day, you know it gets soft. The forces of attraction between them are not huge. It is something that we can melt, and we can overcome that force of attraction by giving it enough energy to break free. But because it's such a big molecule, it's hard for them to move. So they do tend to stay in position. Okay. Now there are some molecules that are a little bit different. Okay, the force of attraction that holds particles together in solids and liquids is due to charge. Okay, so the reason crystals are solid is because there's a great attraction between positives and negatives. The reason O2 molecules tend not to stick together, there's one O2 molecule, there's no charge here. Okay, the electrons are bound next to the protons, everything there looks good. So this doesn't have any charged ends to attract another O2 molecule. So these things have very low forces of attraction. They don't attract. Okay, molecules, just like I said, not charged, not very strong attractions. Okay? Some molecules, though, do have some pretty good attractions, and water is actually one of those. Water is a very, very small molecule. We should expect that water is a liquid at room temperature, but it's not. Or a gas at room temperature, but it's not. It's a liquid. And the reason water is a liquid is because it's does this unequal sharing thing. Hydrogen has 1 proton, oxygen has 8 protons. Oxygen is able to be an electron pig. It can pull hydrogen's electrons closer to it, more towards it. The electrons spend most of their time with oxygen and not very much time over here with hydrogen. Well, if you think about that, that sort of leaves the hydrogen proton a little bit naked. It's exposed. Okay, so this side of my water molecule tends to be a little bit positive. And since all the electrons are piled up over here, this side tends to be a little bit negative. Now, the electrons are still in a shared orbital, so it hasn't actually formed an ion, but it has formed what's called a polar molecule. And because of that, when another water molecule comes by, it's going to have that similar thing, a negative and a positive side. Well, there's a little bit of an attraction between there, and that's going to hold this together, which is why water's a liquid at room temperature instead of a gas. Methane, CH4, okay, has one carbon atom and four hydrogen atoms. This is a nonpolar molecule. It is about the same size as a water molecule, but it's a gas at room temperature because there's very, very weak forces of attraction because the electrons are shared pretty equally here. There's no one side that gets the electrons more than the other. Okay, so when these things are got this unequal sharing, they act like little magnets and they stick together. Okay? And so the polar compounds are going to have higher melting and boiling points than a similarly sized nonpolar compound.